Okay, so how are you all doing? So if it's been a little while since you last had me lecture to you, so let me remind you where we were. So where we're going is we're going to write down supergravity theories, and today I'm going to start writing down lots of theories with lots and lots and lots of indices. All right, so be prepared. And before that, we were talking about some geometry, and I introduced this idea of a G structure. So let me just remind you what that was. So there was a formal way of thinking about it, which was to say it was a subbundle of the frame bundle, which was a principal G bundle. That was a bit over formal. Really, we can think about it as essentially a set of, might be more than one, invariant tensors. Sorry, this is. So I'll call one of those invariant tensors capital Xi. So you know a really familiar example of this where this is a metric. So you have a manifold, and on the manifold you put a metric. That's a particular type of tensor, a symmetric tensor. This could be an anti-symmetric tensor, and then you'd be putting a almost symplectic structure on the manifold. This could be an almost complex structure, and so on. And then we had this notion of torsion-free. Torsion-free structure. And that was the same as there exists a connection, nabla, such that the derivative of whatever structure you had was zero. That's compatible. And the torsion of this connection was zero. So again, you're very used to that idea in ordinary Riemannian geometry. This is a metric. The derivative of the metric vanishes. It's torsion-free. That's the Levi-Civita connection. So what we're interested is doing that in a more general way. So let me now just mention a series of examples. And in general, the existence of a G structure, the first thing, that can put a topological constraint on this manifold. Not all manifolds admit the G structure. This thing is some kind of differential condition, and again, not all manifolds necessarily admit it. And unlike Levi-Civita, you may be that you don't have a unique connection. So let me just remind you of some examples. So if we have the orthogonal group, so if we have an ON structure, that was the same as having a metric, GMN, and there was no topological constraints. So all all manifolds admit metrics, and there was no obstruction to torsion-free, and this connection is just the Levi-Civita connection, and it's unique. So that's the story you're familiar with. Then another example is if we're on an even-dimensional manifold and we have a subgroup complexified matrices, which are a subgroup of real matrices of twice the dimension structure. And that's equivalent to having a tensor with one index up and one down, which has the property that if you square it, you get minus the identity. And this is playing the role of like I, something that squares to -1. This is called a almost complex structure. And it does restrict the topology. And If you want there to be torsion-free, so that's if and only if some tensor, which is called the Ninehouse tensor, this thing has to be 0. So what is that thing? So let me tell you what it is. Don't worry too much. I'm just trying to tell you that there's some condition. So this thing is built out of the i's. So it's m r, and then the derivative along p of I r q minus the derivative along q of I r p minus I r q times the derivative along r of I m p minus, sorry, this should be p, p q, I r q, derivative along r, I m p. So this is just exchanging m and p each time. So it's not obvious that this is a tensor, right? Because these are ordinary derivatives. Turns out it is a tensor. And this is the thing that has to vanish. So you get a differential condition in order for there to be a torsion-free structure. Does that make sense? And if this is true, then you have a complex structure. And what it means is you can introduce complex coordinates on the manifold. So in general, you can't introduce complex coordinates consistently across the whole manifold because you have to patch complex coordinates to complex coordinates. In general, you can't do that, but if you have this structure and if this Ninehouse tensor vanishes, then you always can. So how does that work? So we have complex coordinates. So I'll call them Zi and Z bar I, bar. So I is running from 1 to n now, right? Because I sort of have a 2n-dimensional manifold, so in complex coordinates I'll have n of them. And you can think of them as Z1 is x1 plus ix2, Z2 is x3 plus ix4, etc. And how does this work? Well, if you remember the I, right, we can have holomorphic, so we can have eigen vectors of the action of I. So we could have something which we'll call V10, and if I acting on V10 is I V10, so this is a vector, I can act on it with this thing by contraction, right? I just take the vector, I contract on this index. And I can have another set of vectors which have the opposite eigenvalue. So this, on these vectors, this action of I is acting like just multiplying by I. And in these coordinates, you can write V10 as V10I d by dzi. So these zi's form a basis for vectors of this type. And here V01 looks like V01 I bar d by dz bar I. And the conjugate variables form a basis for these ones. Am I making some sense? Yeah? Yeah. It's not stupid. As a teacher, I have to say that no question is, yeah. Yep. That's one way we can write it, yeah. Yeah. We can choose coordinates so it looks like that, or choose a basis so it looks like 0, 1, minus 1, 0. That's locally, yeah. Yep. I'll have to patch them around and like, yeah. So it's the same way that if you want to, at any one point, if you had a metric, you could always choose coordinates so it looks just like delta ij. Delta mn. Yep. So we don't know that classification problem. We would love to be able to say which manifolds admit an almost complex structure, and there are some famous cases that we don't know whether they do or not. So like no, so we don't know in general. Yep. Any other questions? Okay, so let me tell you about another one. So, yeah. So, of these guys? So what I'm saying is normally we had coordinates xm on the manifold. I'm saying you can always find complex coordinates where I think of them as pairing a pair of real coordinates. And if there are 2n of these, there'll be n of these. And these guys are literally just the complex conjugates. So this one is just x1 minus I x2. Yeah, that's all I meant. Yeah. Any other questions? Okay, so I promise this is going to be useful for you. So let's do another example. Why the 9-house tensor tells you this? Okay, there's no reason that that should be obvious to you. So one way of saying what the 9-house tensor is, so I told you that if I complexify the tangent space, I have to think of complex vectors. This decomposes into 2 bits, which are these 2 kinds of vectors I'm talking about here. And these have a plus eigenvalue and these have a minus eigenvalue. So the vanishing of that tensor is equivalent to, so n equals 0, is equivalent to saying if I take the Lie bracket between u and v, this is always in sections of this space for all u and v that are sections of this space. So if I take any 2 things in here and I take the Lie bracket, then it stays in here. They form 2 separate bits, and that's why introducing these coordinates, that's where that's coming from, right? Because if in some sense u had a bit like d by dz and a bit like d by dz bar, when I take the bracket, it's not necessarily going to stay in this, but if it doesn't have that bit, then yeah. On any given patch, I can always introduce, well, let me not say that. Yeah, maybe that helps. This involutivity condition is equivalent to that. Any other questions? Okay, so let's do another example, which is when I have the symplectic group 2nr inside the general linear group. And this is equivalent to having a 2 form. And I have to have that omega, wedge, omega, wedge, omega. If I do it n times, this has to be non-zero. So that's some non-degenerate condition. Okay. This is called an almost symplectic structure. And again, it's a topological obstruction. It's topological condition. I should have said here, torsion-free, the nabla is not unique. So unlike the metric case, if I can find a torsion-free compatible connection on a complex manifold, there's not just one of them. There's many I can write down. They're sometimes called different things. Anyway. And then here, if it's torsion-free, this is equivalent to the condition that this guy is closed. D of omega is 0. So remember, that just means I anti-symmetrize on 3 indices. And then we have a symplectic manifold. And again, this is obstructed. So that's what this is saying. You have to be able to find a closed 2 form, and nabla is not unique. Yeah.
When we say we cannot have a complex metric,
Yeah.
Is it also saying that we cannot analytically continue any of the coordinates in the metric?
If we don't satisfy this condition, yeah, it's like trying to analytically continue across from one patch to another. And the problem is the patching is such that you can't do that. So on any one patch, you can do it, okay? But you can't, yeah. It's to do with the topology, yeah. I meant to say, you asked a question yesterday about Mobius strips, and I felt unfair that I told you just to keep thinking about it. So we can come back to that at some point. I didn't mean to. What you want to do, right, let me just say, you have a Mobius strip, you want to break it into patches, you want to say, how do you patch on this patch? And then if these guys overlap, how do they patch from there to there? And then the question is, if you did it twice or something, can you find an equivalent patching to something that's trivial? Or can you not? Yeah. I'll give you another hint, which is that the group O1 is really just Z2, right? All you can do, if you're in one dimension and you're doing rotations and reflections, there aren't any rotations. All you can do is one reflection and go back again. So, don't know if that helps. All right, sorry. So these symplectic manifolds are what appear in classical mechanics, if you do it in Hamiltonian mechanics, right? So you should care about them. So let me do one more example, which is going to be a UN structure. So a UN inside GL 2NR. I don't quite know what to call this. I'll call it an almost scalar structure. That's technically not what an almost scalar structure is, but don't worry. This is equivalent to having two things. I need a complex, almost complex structure and an almost symplectic structure. And the reason for that is if I think about the embeddings, I have GL2NR. Inside there, I have a GLNC. That's like a almost complex structure. I also have an SP2NR. That's like the symplectic structure. And there's a common subgroup here of these two, which is unitary. And that's when I have the pair of objects. So I told you that the structure might be defined by more than one invariant tensor. That's what goes on here. And it also defines a metric. And the metric I can write, and again, there are different conventions, so let me hopefully use something consistent. I'll write it as minus omega MP I P N. And it defines a metric because since the UN group is actually a subgroup of O2N. A metric structure would be an O2N structure, right? If this is a subgroup of this, then it must at least define a metric. Am I losing you, or are you okay? Okay, and then, so I'm telling you here what a Kähler manifold is. I'm going to tell you what a Kähler manifold is. So I'm good. Let me get there in a second, then I'll come back to you. Okay. So if it's torsion-free, what we need is we need the Nine-House tensor to vanish, and we need d omega is 0. And then we get, this is what a Kähler manifold is. So a Kähler manifold is a torsion-free UN structure. Or it's a manifold that admits a torsion-free UN structure. Okay. So again, there's obstructions, right? Because there's an obstruction to this, there's an obstruction to this, and there's an obstruction to finding solutions to these equations. And here, because we know that there's a unique orthogonal connection, and a unique connection on here, so this means this one will also be unique. And it has to be equal to the Levi-Civita connection. Because it also has to have, because by definition, because if I have this is 0, that tells me that this is 0, and it's torsion-free. So that means it has to be the Levi-Civita. Yeah. Excellent, yes. So specifying the metric alone is not enough. So I can specify either these two, or I could specify the metric and I, or I could specify the metric and omega, but I always have to specify two things. Yep.
So we know that the metric must be
the connection for it. Given the metric, the connection will be unique.
I'm struggling to see why the unique connection for the metric results in a unique connection for omega and I.
So think of it the other way around. Suppose I have an omega and I and it satisfies these two things. Then this will have to satisfy this, and it's torsion-free. So you have no option.
So in the case of the symplectic manifolds, is the non-unicity of the connection classified? Like, do we know up to what the connection is?
Yeah, essentially. So it's just some representation theory. So the difference between any two connections is a tensor, and then you decompose that under the group, and that will tell you what the freedom is, basically. So yeah, we know essentially what the freedom is. Yeah. All right. So we're going to come back to these Kähler manifolds, and we're also, if we at the end we're talking about supersymmetric backgrounds, we're going to come back to generalizations of them. All right. But I wanted to introduce it here so you knew roughly what they were, and I'll tell you more about them as we go on. Are there any questions? All right, so all right, so now I'm going to finally go back and start telling you about supergravities. Okay, we got there. So let's do it in the most simple cases. So I'm going to start by just telling you about four-dimensional minimal supergravity. Yeah. Yeah, good. Yep. Yep. So that means, so say I have a complex structure, I want to change it to another complex structure, but if this one has n equals 0, this one better also have n prime equals 0. So the problem is, and generally you want to change it smoothly, infinitesimally. So the question is, how can I take this guy, deform it to one nearby, and still preserve this condition? And in general, that gives you a moduli space. So that's a set of complex structures that are all torsion-free that I can put on a given manifold.
Like geometrically, if you think about the formation of K-less structures,
Yeah.
at some point is dimentric.
Yeah.
If I consider the torus, I am deforming somehow. This is my geometrical interpretation.
Yeah.
I don't have a geometrical interpretation for the variation of the
So if you like what I did, I had these complex coordinates, and I want to introduce a new set of complex coordinates, which sort of look like the old ones, but they get a little bit of the complex conjugates into them. So how can I change coordinates so that I put a little bit of the complex conjugates in, but this is still satisfying this? So what you're doing is you're mixing in a bit of the anti-holomorphic bit. All right, so as you can probably tell, I'm kind of teaching you supergravity in a slightly strange way. So the reason is there's a bunch of stuff around supergravities, which is you write them down and you work incredibly hard to show that they're supersymmetric. I don't think that's particularly helpful for you to see. Okay, I think it's more helpful at this point to know that these theories are supersymmetric, but understand what structure they have. So I'm trying to tell you a bit more about the structure of the theory than all the details of proving that they're supersymmetric. Okay, that's the idea. So let's just start, though, with the simplest thing. So let me start with the simplest one that you might think about. And roughly, I'm just going to write down what the theory is and then kind of unpack it for you. And then I'll talk a little bit about where it might come from. So we're in 4 dimensions. And if you remember, we had the gravity multiplet. So this was just looking at representations of the rigid supersymmetry, right? And it had this thing that was sort of spin 2, and it had this spin thing that was spin 3 halves. So this was spin 2, and this was spin 3 halves. And what we want to do, and we already noticed, so we noticed that psi-m, the psi-m equation of motion, had a symmetry where we shift it by gamma m times something, and this could depend on the position. So it had something that looked a bit like we could make a local supersymmetry transformation. And what we're trying to do is we want to go to a nonlinear theory with gravity and local supersymmetry. Right? Gravity, because we said that if you do 2 supersymmetry transformations, you get a translation. And if we want to do local supersymmetry transformations, we're going to have a local translation. That's like a change of that's like a change of coordinates. So we're into gravity. And this is spin 2. So just as a general problem, this is hard, right? So there are theorems, for example, if you want to write down a spin 2 theory. Say you've got spin 2 and you want to make it interacting. It's massless spin 2, you want to make it interacting, you want to make it nonlinear. You don't have any other fields. You can start asking, how many ways can I do that? There's only one way of doing it, right? It's just Einstein gravity. It's unique. So we're adding in this extra spin 3 halves field, which is also going to be somehow hard to introduce interactions. So in general, the sort of feeling is that this is a hard thing to do, and you might think you can't do it, right? There's no guarantee that you can make this a priori into a sensible theory. Yeah. Yeah, so I want a 2 derivative theory which has a spin 2. Yeah. Yeah. Oh, sorry, yes. I'm sorry, yes, thank you very much. This was the derivative, right? Yeah, thank you. Okay, so let me just tell you what the theory is. So here's the theory. So I'll write down the action. It's got some gravitational coupling, which I'll write as a 1 on kappa squared. That's the standard thing you do. And this is like big G, right? We're in 4 dimensions. We have an integral with a measure that's given by the square root of minus the determinant of the metric. And then I have some curvature term. If this was ordinary Einstein gravity, you just write down the Ricci scalar here, right? I'm going to write down the Ricci scalar, but for some connection nabla, which is not yet the Levi-Civita connection. In fact, it's not the Levi-Civita connection. And then I'm going to write a term which looks like the... So now I'm going to write down a term for the gravitino. So I should say this is... So we've got a metric GMN and a gravitino because it's the partner of the metric of the gravity, which I'll call psi. And I'm going to write some derivative here, which I'm going to have to tell you about. Okay, so at the moment I've got 2 derivatives sitting in this action. I've got this nabla here and I've got this derivative here. Okay, so let's just remember what we have. So we have the Levi-Civita connection. So that, if I took a derivative of a vector, right, that's the thing that you're used to. This would be, and these are the Christoffel symbols. Assume everyone's happy with that. And if I write it in a frame, so where should I go? Let me go over here. We have a metric. So that's equivalent to an OD structure, or sorry, an O31 structure. So we can introduce orthonormal frames. Right, so I can have, I'll write them with a hat down like that. So these satisfy G, Mn, E hat Ma, E hat Nb is eta AB, where this is minus 1, 1, 1, 1. Right, this was just like the G structures we talked about. There I talked about On, now I'm doing it with a different signature. So I get the Minkowski metric here. Is everyone happy? And there's a dual frame, EAM, which satisfies EAM, E hat MB is delta AB. And if I write the vector in, so in an orthonormal frame, I can write my vector as VA E hat AM. And when I take the derivative of these guys, I get something like the derivative of this. And then here I'll get the connection, but in the frame. So let me call that little omega. I'll put Levi-Civita here to remind ourselves, A, B, VB. So that's the connection as written in the frame. This is the connection as written in the coordinate frame. Is that okay? And just so you have it, what's the relation? Well, the relation between these two things, the Christoffel thing and this thing is sometimes called the spin connection. It's just the ordinary connection written in an orthonormal frame. Just the Levi-Civita connection in an orthonormal frame. And to give you the relations, so MB, I can raise and lower A, B, C indices with eta AB, right? Because they're orthonormal with respect to the eta. And I can raise and lower M and P indices with the metric GMN. Okay? So if I write beginning of the alphabet indices, those are orthonormal frame indices. If I write middle of the alphabet indices, those are coordinate indices. Is everyone happy? So let me write this guy, let me raise this index with an eta. And then this Levi-Civita thing is just, if you want to write it in terms of the frame, it takes the following form. So hat N A D M E N B. So when I write square brackets, I'm anti-symmetrizing everything. And then I get another term which looks like E hat N A E hat B P E M C D N E P C. So all I'm trying to say is I can write this guy in terms of the frame. Okay? You can work that out if you want.
On the second part of the expression,
Yep.
what is regarded to different indices on the second frame?
B and P.
So which ones are related to
So when A and B are at the beginning of the alphabet, so they're the frame indices, and the P is at the end. I just switched those around so I could write the anti-symmetrization. Sorry, yeah, that's a bit confusing. But the nice thing about using the frame, right, using the frame, so using the orthonormal frame, we can take derivatives of spinors since spinors are spin 3-1 representations, right? So what I mean is, if I have a vector, I have the derivative of a vector is dm va plus omega m ab vb. And if I want to take the derivative of a spinor, this thing is acting in the adjoint. This is acting as the adjoint representation, or this is acting in the vector representation of O31. This thing has the property that it's anti-symmetric on these indices. So you should think of it as like adjoint valued. right? The Lie algebra of SO31 is something which is anti-symmetric when you lower the indices. So that means you can also act on this, and you just need to use the corresponding representation. So now I can do the following. Sorry, epsilon. I can use the gamma matrices because the gamma matrices give me a spin representation. So once I've got things using the spin connection, I can then act on any representation of, in fact, spin 3-1. So the advantage of writing things in the orthonormal frame is that everything comes in representations of O31, and hence I can promote them to representations of spin 3-1, and I can take derivatives of spinners. And the point was that the symmetrized gamma matrices were the things that generated the spin representation. Okay? Okay, did I erase the thing I shouldn't have erased? No. Okay, good. All right, so let me tell you, so that was all this was all Levi-Civita. But you can extend this to any O31 compatible connection. Right? It doesn't have to be Levi-Civita, it doesn't have to be torsion-free. So let me tell you about what these things are. So what are these connections? Sorry, let me just say, here. So I could also take, if I took the derivative of something spin 3/2, right? It's got a spinor index, which I'm suppressing, and it's got a vector index. So this should look like the derivative like that. Then because it's an index down, I get the Christoffel symbol. And then for the spinor indices, I should get the gamma matrix action. Right? So I'm treating it as having both something that looks like a one-form index or a vector-like index, and it's a spinor, so it gets derivatives in both bits. So M and N are the vector indices written in a coordinate basis. So I'm just using coordinate. A and B are vector indices written in a frame basis. And then the gamma matrices act on the spinor, and they kind of give me the spin representation. Yes. So let me be more explicit. If I write an alpha there, and then this should be alpha beta psi n beta. Yeah, exactly. Thank you.
Why did we use omega in the second element?
Here? So, okay, so this is just my index stuff. So if I'd written this with an A index as a frame index, which I could change, then this would be an omega m minus omega m b a psi b alpha. So it's just that I chose to write it in a coordinate basis rather than a frame basis. And we have this convention that we call the connection something different depending which frame we're in, which is a bit weird, really. You should really just call them the same thing, right? But that's what everyone does. All right, so here's the action. So what's this nabla? So this nabla M is the Levi-Civita So if I have nabla M acting on Vn, it's the Levi-Civita acting on Vn, and then it gets an extra piece. Or let me do it on, sorry, let me do it on Va. It gets an extra piece, which I'll call K. And what does this K thing look like? So K M A B. It depends on the gravitino. So it looks like gamma M, gamma B psi A minus psi bar A, gamma M psi B plus psi bar B, gamma A psi M. Okay, it's an extra bit. So this is still metric compatible. So this connection is still metric compatible. But the torsion is equal to twice this K thing. Yeah. So this psi is indeed this gravitino. Yeah. And then you have to work out the Levi-Civita curvature using this connection, not the sorry, you need to work out the curvature using this connection, not the Levi-Civita connection. Okay? So somehow hidden in here, there are psi's. And instead of having a torsion-free compatible connection, we get a torsion-full compatible connection. So it's useful because you could have written everything in terms of this guy, right? And I'll do that in a moment. And you get a whole load of terms which look sort of like 4 fermions in them. They'd look like, in the curvature, you get things like connection squared, derivative of connection and connection squared. So you get things that look like 4 Fermi terms. So I could also just expand this out, and I'd have a whole load of terms here that look like psi bar psi, psi bar psi. But interestingly, they package themselves so that they just look like the curvature of a different connection. So there's this sort of natural connection appearing here, which is this one in supergravity, but it's not torsion-free, it's got torsion.
Sorry, can you say it again, how you find this new connection?
So I didn't tell you at all how to find this new connection. So at this point, I'm just telling you, it's an excellent question. I'm just telling you there's a magical theory, this is it. And it's going to be supersymmetric. I will then try and tell you a little bit about where it comes from, how to think about why it exists, and also where this term comes from. I realized we could have a break. Do you want to have a little? Let me tell you one other connection thing, and then we'll have a shortish break because we lost a lot of time. And then, okay. So I told you what this thing living in here is. What about this D operator? So also, and dm psi p is so let me write this as dm psi a plus omega m ab. So, right? So this omega is built out of the Levi-Civita omega plus the k. So you should think of this guy, omega is omega Levi-Civita plus k. What is this other derivative? So this derivative is just dm psi p plus a quarter omega m ab gamma ab psi p, where this omega is indeed this omega. That looks pretty good, except I told you when you take the derivative of psi, you should have two terms. You should have a bit that takes the derivative along the vector and a bit that takes the derivative as a spinner. Whereas here, I'm only keeping the one that takes the derivative as a spinner. Now something really weird happens. Suppose I put in the derivative along here. Suppose I did the full thing. In this action, it's contracted on things that are anti-symmetrized. So it would take this term and anti-symmetrize it. If this was torsion-free, that anti-symmetrization would give you 0. So if this was a torsion-free connection, then in the action here, writing this or writing this with the gamma term would have given me the same answer. But this isn't a torsion-free connection, this guy. So that's not really what's going on. It's almost what's going on, but it's not quite right. So this is almost like writing the covariant derivative, but it's missing a torsion term. So again, if you like, it's just another kind of derivative. I had this derivative, and there's another one that's appearing here. It's not quite the same derivative. It looks like this is the same derivative as this, but it's missing a term to be that. Okay? So the only thing I'm trying to get you to take on board is that we're getting derivatives that are all metric compatible. We're sort of getting different ones. There's Levi-Civita, there's this nabla, there's the thing that appears in D. They're not all quite the same thing. Okay? But it is all perfectly covariant because the difference between any two derivatives is always a tensor. So I can always, it's fine. All right, so why don't we stop for 5 minutes and then we'll keep going.
What are you saying is contingent on me?
Okay, so we have this action and we have these two kind of derivatives that are appearing, these two different connections. So just to say, we can expand out. So what happens then is that you get the following action, and it's going to look more like what this was one of the questions that came up. So now I'm going to get Levi-Civita. I'll get the Levi-Civita curvature there, and I'll get just the ordinary Levi-Civita derivative here. And because this is Levi-Civita, the extra term that was missing there actually gives 0, so it's fine. I can do the full covariant thing. And then you get a whole load of terms in the fermions, so let me just write them down. I get 1/16, and then I get psi bar p gamma m psi n, and then psi bar p gamma m psi n, I hope, plus 2 psi bar p gamma n psi m, and then another term, minus 4 psi bar m gamma n psi n, so that's contracted. So here they're contracted across, here they're contracted within, and psi bar m gamma p psi p. So if you want, you can think about it as ordinary curvature, kind of ordinary kinetic term for the fermion, and then a whole lot of terms in terms of 4 fermions. And I'm using sort of throughout here that if I have a pair of spinors, this thing is equal to minus this thing. So if you ever want to do the calculation, you might need to remember that. But what's interesting is that all these extra terms can be repackaged in that way, right? That's sort of the point. So, yep. So NN contraction, and then PP contraction. So it turns into a total derivative, and so like I'm just saying it doesn't change the action. Yep. It's true that when I expand out that R, there'll be derivatives of K, and that will look like derivatives of things, but it will all cancel out. Sorry, say it again.
We can further generalize this action to write it as a Palatini action.
Yes. Okay, so there's a thing that I was glossing over, is that there's 2 ways of thinking about actions with spin connections. You can think about them just as functions of the frame alone, or you can think about them as functions of the frame and the connection. And they're called the first order and second order ways of thinking about the action. Everything I'm doing here, I'm thinking about it in the second order thing. Everything's just a function of E. You can still write down the same, basically the same action as the first line and think about it in the second order formalism if you want. Yep. Sorry, the first order formalism if you want. Yeah, so everything here, I'm just going to think about it classically, so I'm not going to talk about that. But yes, which things you think of as the dynamic called degrees of freedom can in principle have changes when you start doing quantum corrections. Yeah. Oh, and there's another big one there. Okay, I have to do that. Okay, brilliant. I really like that. Thank you. No, it's good. It's very good.
So, in the end, even though we had something very complicated, we didn't end up with something that is not minimally custom.
Right. Yeah, in this case. Yep.
So all this time we spent talking about the distortion.
Why did I do that? Yeah, go on.
But now we see that there's torsion.
There's torsion, yeah. So, can I come back to that? Yep. Well, let me say, partly I just wanted to introduce the notion of structures and torsion because they appear in lots of different places in supergravity. And then actually for these torsion-free structures, they appear, I think I mentioned, in 2 ways. One way when you try and write down more complicated supergravities that are coupled to scalar fields. You see that the scalar fields look like coordinates on a manifold. Not the manifold, space-time manifold, but just another manifold. And those manifolds get special structures like Kähler structures on them. And then also if I look at supersymmetric backgrounds, I get things with torsion-free structures. So that's sort of part of what I'm saying. I'll say a little bit about superspace, and again, you're going to sort of see a bit about torsion freeness there. Right? So, okay, so I told you this was supersymmetric, so what are the supersymmetry transformations? So I need to parameterize them by a spinner, right? So I have a spinner parameter. And the variation of the frame, I'll write the frame, the dual frame, looks something like a half epsilon bar gamma A psi m. So it depends on the gravitino. The boson depends on the fermion. And the variation of the gravitino is just the covariant derivative of the spinner, where this is that nabla that appeared up there, the one with torsion. And you can see the leading term here is like the derivative of the spinner. That was the thing we saw in the linearized theory. And you can check. If you have a few days and you like doing fits, identities, manipulating gamma matrices, you can go check that that's a symmetry. It's actually not so hard. There are clever ways of doing it. But you also can check that the algebra closes. Right? So if I do the anti-commutator of two supersymmetry transformations, I should get a symmetry. So let's remember what symmetries we have. So our symmetries, well, we have supersymmetry, which is the one I just said. We have diffeomorphisms. So that's when I make a coordinate transformation, right? So I let xm go to xm. Let me write minus psi m. And then I also have, because I have the frames, I have local Lorentz transformations. So that's like I have my frame. So in a frame, I just do a transformation like that. So the components, or equivalently, if I have the frame, it goes to lambda inverse BA times the frame. Okay. So any two frames, right, are going to be related by some Lorentz transformation because I'm doing a O31 structure. Does that make sense? So when I do the algebra, it should be that when I do two supersymmetry transformations, it comes back to a combination of symmetries. So that's what happens, but it does it in quite a not totally straightforward way. So you find that if you do the anti-commutation of two supersymmetry transformations, I find that I get a diffeomorphism. I also get a local Lorentz transformation, and I get another supersymmetry transformation. And to do this, to see this, you need to use the psi m equation of motion. So this is what's called the algebra closes on shell. So the way I've written this down, this action is invariant under supersymmetry transformations. The supersymmetry transformations anti-commute into other symmetries, provided I use the equations of motion. Okay? And what do you find? You find that the diffeomorphism looks like a half epsilon 2 bar gamma m epsilon 1. So that's kind of what we expected, right? You do the anti-commutator of two supersymmetries and you get a translation, a local translation. But it turns out you also get a Lorentz transformation which depends on this spin connection. So this is field dependent. And then you also get another supersymmetry transformation, which is given by this guy contracted into the gravitina. Yeah.
That's a nice question. Is there another formulation of this action which is equivalent as
Absolutely. So you can go off shell and you need to introduce some extra fields called auxiliary fields. And you can write down an action with the auxiliary fields and transformations of these two and the extra fields. And then you can show the algebra closes without using the equations of motion. And that's a much more powerful formulation because you could, this whole thing comes as a package. It's supersymmetric with this action, those transformations, because I need the equations of motion. What you'd like to do is have something where I just have some symmetry and I can then start trying to write down all the actions that realize that symmetry without having to use the equations of motion. So if you wanted to think about corrections to this action, like that depends on higher powers of R, for example, you want that off-shell formulation where you don't need to use the equations of motion. Yep.
Maybe I would have expected to see like a variation of the graviton, like G and then
Yes.
those we did. We wrote E, and is it physically okay if I think about this as a graviton?
Yeah, so let's think. So the graviton, I can write the graviton, the GMN, as eta AB EAM EBN. So if I do the variation of this guy, it's going to be twice the variation of EBN. And then I can substitute, and this is actually going to look like epsilon gamma, 1/2 epsilon gamma m psi n plus epsilon gamma n psi m. So from this, I can get a variation of the metric. Yeah.
My question is this more fundamental?
In a sense, it is because in order to write down the spin connection terms, we needed a basis. So so I really need to think about the variation of the basis rather than the variation of the metric.
In a representation theory way of thinking about this, we had the Sufi algebra,
Yep.
and we had this graviton multiplied supermodel.
Mm-hmm.
Now we wrote the action and we find that there is something else which seems to be more fundamental.
Right. So if I count degrees of freedom, it's the same number of degrees of freedom, because I can always do Lorentz transformations on this, and so I've just sort of repackaged it in some sense. Yeah, but that's a very good question. Other questions? Yeah. Yeah. Yeah, as written, I don't know quite what to do when I do the quantum theory. Yeah. But I'm sort of not telling you anything quantum yet. Other questions? Yeah.
I'm a bit confused by the source of these local the symmetry that is the local Lorentz transformations, because some of this seems to be an artifact of choosing the orthonormal basis, right? Because if you choose some other basis, then the symmetry won't be there. Or am I thinking of this?
So in order to write down the, so it is. So it's a fact that I've got a metric. It's a property of the fact that I've got a metric and a G structure. So there is a preferred set of bases, which is the orthonormal ones. So, and I need that orthonormal basis in order to write derivatives of fermions.
But
That helps.
Like we didn't see this in regular GR. Over there, we only talk about different morphisms.
So you can formulate regular GR using a basis and the spin connection. And then it has two sets of symmetries. It's got local Lorentz transformations, and it's got diffeomorphisms. And they sort of talk to each other a little bit. I mean, you can do diffeomorphisms, you can do combinations of the two, and they will interact. Yep, yep, yep.
I know that there are some supersymmetry theories that to avoid this problem of the algebra closing on only on shape.
Yeah.
Works with some auxiliary fields.
Exactly. Yes. So there is a formulation, and just because of time, I'm not telling you about it. There's a formulation here where you introduce extra auxiliary fields in the supergravity. There's actually more than one way of doing that. And when you do that, that allows you to close the algebra off shell. Yep. Any other questions? Okay, so let's see, if I go a little bit over, that's probably okay, right? We can have lunch a little bit late. I won't go too far over. So let's do this one. So as stands, this was a slightly mysterious construction, right? I just gave it to you. I should say, you know, this was worked out by Friedman, Ferrara, and van Neuenhausen in the 76, right? So it's kind of amazing that they did it, right? It's really incredible. So why does this work? So let me give you a bit of a hint about why this works. So I want to talk about, and we won't finish it, but I want to talk a bit about superspace and G structures, because I can't help it. So why does the supergravity exist? Or put better, can we think, is there a better geometrical understanding? So in principle, we might think we couldn't write down any interacting supergravity theory. It's not obvious that you're going to be able to do that. So if you remember, we had super Poincare, and we had translations in the super Poincare. We had translations, which was sort of x mu goes to x, so xm minus m. And we had supersymmetry transformations. And there's a way of thinking about these geometrically. So we can sort of geometrize these. And we do something really weird. We think of them both as kind of, we expand our notion of space-time. And they're going to correspond to super diffeomorphisms. So we're going to try and think of these supersymmetry transformations as like translations, or like some diffeomorphism. So I'm just going to sketch how you do this. So what happens, so we're now going to introduce coordinates, and I'm going to have xm, and I'm going to have some spinor coordinates. Or maybe I shouldn't say spinor yet. I'm going to have some extra coordinates. And I'm going to have translation, and I'm going to have super diffeomorphisms. Which is going to be xm goes to xm minus some sky, which is a function of both sets of coordinates. And I can also change my thetas. So the idea is this is a little bit like a supersymmetry transformation, right? There's a spinor parameter here. But these guys, but the theta are anti-commuting. So theta alpha, theta beta is minus theta beta, theta alpha. Because we're going to need anti-commutators in the symmetry algebra. So this is something called a supermanifold. And these are called superspace. So, and I can think of a coordinate here, I'll call it Zm, and it's built out of this pair of things. So for the moment, just hold your breath and imagine that you can build some manifold which has regular coordinates and anti-commuting coordinates on it. What might that mean? So if I have a, so what does this mean? Well, if I think about a function, phi of Zm, I can do a Taylor series expansion, right? I can do a Taylor series. So phi of xm theta alpha is phi 0. I'll do a Taylor series in the thetas. Yeah. Second? Excellent. Sorry. So alpha here is going 1, 2, 3, 4, and it's like a four-dimensional spinor. Because in the end, I'm going to want to think of it like a spinor. Yeah, brilliant. So if I do a Taylor series expansion of this, this is going to terminate in the thing with 4 indices because I only have 4 different thetas. And this one has to actually just equal theta 1, theta 2, theta 3, theta 4. So if you want another way to think about this, you can almost think of ordinary manifolds with above each point like a Taylor series expansion. But there's a way of formalizing this, and you might think then that the natural way to do supergravity is that we want to do the analog of Riemannian geometry now on this supermanifold. Because we had ordinary translations, now we have these things which are like super translations, and we want to make them now into local things. That should be like doing Riemannian geometry. So we might expect that supergravity equals super Riemannian geometry. I.e. sort of super Einstein. You can make your own joke. Right? We sort of want to introduce a metric on this big space, write down curvatures, write down the analog of Levi-Civita. That might be the supersymmetric theory. Actually, this is not quite what you do. So I'm conscious of lunch. So you actually look for a spin 3-1 structure. So we're back to G structures again. Why don't I tell you a little bit and then we'll come back to it next time. So how does this work? So if I have the tangent space at the point Z to my supermanifold, script M is a supermanifold. This is isomorphic to just, I'll write it like this. This is the way people write it, 4R44. So this means I have 4 commuting directions and 4 anti-commuting directions. Right, so these are like the d by dxm's, and these are like the d by d theta alphas, if I'm using some coordinate basis. Okay. So if I introduce a frame, so I can have a frame where now this is running over 8 directions, right? Because it has to, this is an 8-dimensional space. It will also have a kind of both commuting bit and an anti-commuting bit. So sorry, I should have used mu for this. I'm really sorry. Okay, everywhere there was alpha beta, it's now mu nu. So I'll try and use mu for coordinates and alpha for frame. So we had m for coordinates and a for frame, and now we have mu for coordinates and alpha for frame. So the frame will split into a bit that's like in the commuting bit of the frame and a bit that's the anti-commuting bit of the frame. And in general, another frame will be some rotation of this. And this matrix has to be an element of what we'll call GL 4/4. What that means is it looks something like this. It's going to have a bit that's commuting here. I'll write B for boson there, fermion there, and fermion there. Because if I want to take an anti-commuting thing and keep it anti-commuting, I multiply by something commuting. If I want to take an anti-commuting thing and make it something commuting, I multiply by something anti-commuting. So these are like general linear transformations, but you have to think of them in blocks with commuting blocks and anti-commuting blocks. So this was the analog of GL4R that we had in the ordinary geometry. Now I have this extension because I have these extra anti-commuting directions. And now really I'm going to have to think of G structures here, some G structure, which will be some subgroup of this group. And the trick that I'm going to do is just take a G structure where I just turn on these bits and I make it just into the spin group, with this acting like the vector representation and this acting like the spinor representation. Okay. All right, so why don't we stop there and have some lunch, and then tomorrow I can tell you more about that.